remind you what we did last time. We started talking about Gaussian integers. It was, well, Gaussian integer is something like x plus I times y, where x and y are integers, and I is the imaginary unit, square root of minus 1. Some kind of number that we pretend that exists. And we did funny things with them. For example, we factored them into products of other Gaussian integers, and we've seen such examples. 2 plus I. Well, this number cannot be factored into the product of two Gaussian integers which are not units. We call that units are plus minus 1 and plus minus I. In Gaussian integers, they play the same role as unusual integers with plus or minus 1. You can always multiply, well, in any factorization, you can change, well, if n divides some number, then minus n also divides it. So the same here. If some z divides a given number, then I times z divides it, minus z divides it. So units are not interesting divisors, but this number cannot be factored as a product of two non-units. So this can be factored as product w or w non-units in Gaussian integers. So does anyone remember why it is not a product? Yeah. Well, almost 3. It's 2 squared plus 1 squared. So it's 3 squared plus 3 squared. So this is 5, yes. And norm is multiplicative. Norm of z times w is definitely product of norm of z and norm of w. So if 5 is a product of two numbers which are norms of something, one of them should be 1. And if norm of a Gaussian integer is equal to 1, the Gaussian integer itself must be a unit. It must be 1, minus 1, I, minus 1. Okay. Thanks. So another thing, let's say I start with the number 5. Well, in usual integers it is a prime number. Is it a prime number in Gaussian integers? Is there a way to factor it as a product of two Gaussian integers? Well, maybe somebody can tell me what is the norm of 5. Yes. So norm of any number of x plus iy is x squared plus y squared. This is 5 plus 0 times I. Its norm is 5 squared plus 0 squared, which is 25. It can be factored as 5 times 5. So there is a chance that this number is the product of two Gaussian integers. Each one of those is norm 5. Well, what Gaussian integers have norm 5? Yes, here is one of them, 2 plus I. So maybe let's try it. If you take 5 and divide it by 2 plus I, so what we call how the division, we multiply and divide by the conjugate expression. So again, 2 squared plus 1 squared is the denominator. So we get 2 minus I. So indeed 5 can be factored as a product of two things which can't be factored further. It's 2 minus I times 2 plus I. So in usual integers 5 is a prime number. In Gaussian integers it is a product of two prime numbers. This number, well, cannot be further factored. This number cannot be further factored. The 5 can be factored. It's not prime. Okay, so we talked about the possibility of always factoring the number into a product, Gaussian integers into a product of several numbers which cannot be factored any further. Let me apply this idea to a familiar problem, to parameterize Pythagorean triples. So Pythagorean triples if you recall, we are trying to solve such an equation, c squared plus a squared plus b squared. What's good about it, we already know the answer, so once we get a new answer, we'll be able to compare. So here we have an equation. On the right hand side, you see that it's, well, it can be factored as a product. It's a plus b. Well, maybe first let's make usual assumptions. We can assume that a, b, and c don't have any common factors. So assume GCD of all three is equal to 1. That's a pretty safe assumption. It's not 1. There is a common factor. Just divide a, b, and c by this common factor and get the triple without a common factor. Another thing, well, maybe it's important, maybe it's not really, but here you know that, well, that either a or b should be, well, if a is if a is odd, then b must be even. It's not possible that both a and b are odd numbers here. And the reason was because the square modulo of 4 is always congruent to 1. So if you have here 1 modulo of 4 and 1 modulo of 4, this will be 2 modulo of 4, and 2 is not a square modulo of 4. So you can also assume that a is odd and b is even. I mean, one of them must be even because of these things, so we can assume that b is the even one. Okay, so this has nothing to do with Gaussian integers, but now let's rewrite this equation in the following form. C squared is a plus ib times a minus ib. Well, now I factored the right hand side, and now I have two different factorizations of the same, well, not just Gaussian integer, but in particular Gaussian integer. One factorization is c times c, another factorization is a plus ib and a minus ib. Moreover, I can say something about the GCD of these two numbers. What is, can they have any common factors? Well, let's see. The GCD of this and this, well, if something divides both of them, it must divide the sum. So it's the same as GCD of a plus ib, and the sum, which is twice a. So this is just the sum. A plus ib plus a minus ib. Now, can 2 be a divisor of a plus ib? Well, let's see. b is already even, so if it divides a plus ib, it must divide a as well, but then, well, a is assumed to be odd. So it's in fact 2 cannot be a divisor of this thing, so it's the same thing as GCD of a plus ib and just a. And finally, well, if something divides this and this, it divides the difference. So it's the same as GCD of ib a. And well, I is a unit, it's like plus or minus sign. If something divides ib, it divides b itself. So it's the same as GCD of b and a, which we assume to be 1. We assume that, well, nothing divides both a and b. If it divides both a and b, it must divide c as well. And then we assume that there are no common factors. Yes?
How can we define what GCD two Gaussian integers is? Like, what is greatest?
Okay, so we indeed didn't define it, well, not explicitly, but we kind of have it. We can factor a Gaussian integer into a product of irreducible things, and then compare the, well, if you have factorization of one of them, factorization of the other one, we'll just take all the common factors. And then under the GCD, it is defined up to multiplication by units, but well, kind of defined. Okay? Yes?
So it's also could be like, if we say GCD is I.
So saying GCD is I is kind of saying, like in usual numbers, GCD is -1. So for example, what is the GCD of, say, 5 and minus 3? Is it 1 or is it minus 1? So it's kind of that stuff. So in Gaussian integers, yes, the GCD is not once again defined precisely. It could be, well, if I get a number which is 2 plus I, if 2 plus I divides both A and B, then you know that minus 2 plus I divides both A and B, and you also know that I times 2 plus I divides both A and B. So there is kind of, GCD is not really unique, but still, there is a meaning. Well, if this phrase makes sense, it means A and B are relatively prime, or these two numbers are relatively prime. Okay. Yes?
Also, have we proved that the Gaussian integers have unique prime factorization?
No, we didn't.
Because that's kind of important for this.
It is very important, yes. So that's probably the main point of today's lecture, to say that it is important that we have unique factorization, but it's kind of subtle point. So here I want to assume it. So to be honest, I'm doing this to kind of showcase what we can do with Gaussian integers. Then I'll try to convince you that it's not that obvious, and then I'll try to convince you that we can actually justify all the steps here. Yes?
How do you order something high?
Sorry?
How do you order things with high?
Well, should I order them? So I'm never comparing two complex numbers.
So it's just greatest.
Yes, so greatest common divisor means, well, so greatest common divisor. Okay, so maybe I should make a definition of what greatest common divisor is. We say that the greatest common divisor of two numbers is C if, well, two properties. One, it is a divisor, and the other one is if we have some other divisor which divides both A and B, then C is the divisor, then D divides the GCD. So it's greatest in the following sense. Among all the divisors, it divides all the divisors. It is divisible by all the possible divisors. This is a definition. It is true in integers, it is valid in Gaussian integers. It is a definition of what we mean by GCD. So in usual integers, we could have said that it's the largest in the usual order, but it would be a wrong definition actually, because if you take instead of the number minus the GCD, it still satisfies all the properties of GCD that we actually want. So when we say greatest, we mean that it's divisible by all the divisors which divide A and B. So that's the meaning of greatest. Okay. And well, kind of procedurally, what we want from GCD is if we factor these two numbers as a product of things which cannot be factored any further, we just take all those which appear in both factorizations. So if you have something which appears in both factorizations, you include into the GCD. So that's what we want. Okay, so what I want you to do here is convince you that these numbers are relatively prime. No Gaussian integer can divide all this and this if we assume that well, A and B are relatively prime. Okay, so here we have an equation. A square, C squared, is a product of a Gaussian integer and its conjugate. And these two numbers are relatively prime. What can we say about these two numbers? Well, if you have a factorization of C squared, of C, the factorization of C squared will have any prime to an even power. Any prime must appear either in factorization of Z or Z conjugate, not in both, because they are relatively prime. So both Z should be a square and Z conjugate should be a square. So I can say that Z must be a square. Well, then the conjugate is automatically W conjugate square, and then C squared is W squared times W conjugate squared. So C squared is W conjugate squared. Well, hence C should be plus minus W conjugate. Let me choose the positive one. I'll be dealing with positive solution C. So here we got a solution. For any Gaussian integer W, you have a solution here. W squared times W conjugate squared is W conjugate squared. What does it mean in usual integers? Well, it means the following. If W is x plus iy, then W squared is what? This times itself. So it's x squared minus y squared plus 2ixy. And this should be equal to a plus ib. And also we know that W times W conjugate, which is x squared plus y squared, should be equal to C. So we got the parameterization. A is this part, the part without I, the real part, so it's x squared minus y squared. B is equal to 2xy, and C is equal to x squared plus y squared. So here's the parameterization of all Pythagorean triples. We obtained it. First of all, it is correct. It is indeed the parameterization that we had, like in the second lecture, when we did it with the circle or with some other factorization and some algebra. We obtained it, well, quite easily from this factorization in Gaussian integers. The only, well, maybe, well, two ingredients. One is verification of this fact that these two numbers are relatively prime. The other thing is this step. If you know that C squared is the product of two relatively prime numbers, it means that each one of those numbers is a square. So basically, these two very simple ingredients. So you see that first of all, it is very useful to be able to factor over Gaussian integers. We can solve, for example, such problems. And later we will once again use these tricks to answer the question of what integers can be written as the sum of two squares. So we'll answer a much more general question. Not only which squares can be written as sum of two squares, but more general question. What integers can be written as sum of two squares? But for now, let me, so maybe any questions about this? Yes.
Can you tell me why
Yes. So here, if you know that C is a product of some Gaussian integers which are not further reducible, you have such a factorization. Q1 to some power times Qn to some power. Then you know that C squared is product of primes with even powers. Then you know that, oh, in this factorization, each of the primes should appear either in the factorization of Z or in the factorization of Z conjugate, but not in both. Because if one of them appears in both factorizations, well, it will appear in the GCD.
But, okay, so Z conjugate is like a minus I.
Yes, so this is Z and this is Z conjugate.
So if you have like a case like when the B is equal to 0 in that way, so if you have like Z obviously it's conjugate, but this is conjugate and not in the I part, then it's just like a square, but that Z doesn't have to be a square in the
So what we did here, we verified that these two numbers are relatively prime. In the assumption that A and B were relatively prime, these two numbers are relatively prime. The example that you are trying to suggest is, well, when B is equal to 0, and then you have this GCD equal to A. But then A and 0 are not relatively prime. So if A and B are relatively prime, this computation shows that these two numbers are relatively prime. And then no factor of Z can be also a factor of Z conjugate. So, I mean, it's not important even here that this second number is Z conjugate. It could be Z1 and Z2 if they into numbers which are relatively prime. That's what's important. So, in the factorization of Z, every prime factor appears to an even power, so the whole Z is a square of something. Okay, other questions?
You assume that the triples, or the parameterization yields solutions which are not primitive. Because the formula in the first chapter, it's different. Like,
So here I assume that A was odd and B is even. The formula in the first chapter I assume that A was even and B is odd.
so even then you divide by 2 or something like that, I don't know.
So once again, I'm pretty.
Like you can just look this over real quick.
Yes.
It's a different formula for the primitive ones. This is the general one.
No. So if you assume that A is odd and B is even, then these things parameterize all the primitive ones if x, well, if one of x and y is odd, one is even, so then B. I mean, if you have this parameterization, you also have another parameterization. A is equal to x squared minus y squared over 2. Let me call them by different names. B is equal to xy and C is equal to x squared plus y tilde squared over 2. Both parameterizations are correct, but here you assume, well, x is odd, y is even, and A turns out to be odd, and this turns out to be even. And here, as I said, so this one is the even one, this one is the odd one, and you assume that x tilde, y tilde are both odd. So there are two different parameterizations that could parameterize the same thing. It's just that this x and this x tilde are not the same thing. For each x, we can find its own x tilde and vice versa.
What is that zero?
Sorry?
Is it an arbitrary integer?
Well, it's an arbitrary integer, but not all the integers will be primitive triples. But for example, if you take x odd and y even, you're also primitive.
Because we assume this primitive, but then
Oh, yes, so we started with a primitive triple. We proved that every primitive triple is of this form, but we didn't say that every such triple is primitive. And it's not true. And if, for example, x and y are all even, then it's not a primitive triple. You want to make a comment?
Oh, no, I just wanted to say that I think it comes in a step where you went from w to w squared. Like, just again, as long as you choose x and y to be different parity, then x squared minus y squared into 2xy will be different.
So I think that I used the assumption about divisibility by 2 somewhere here, then I went from here to here. Here I made assumption about something not being divisible by 2. And the assumption of A and B being relatively prime is right here. So I actually used primitivity, and I used, well, some constellations modulo 2. And well, I did arrive at parameterization, but I didn't check that for every x and y I get a primitive triple, and indeed it's not true. Every primitive triple is of this form. Okay.
for the converse is opposite.
The converse will, no, but still, we got the parameterization of all the primitive triples. Well, these formulas parameterize a little bit more, but well, not much more. But still, these formulas are always Pythagorean triples, so every Pythagorean. Okay, so we got parameterization. Okay. Okay. Other questions? So now I want to try to do the same kind of thing, but with this equation. C squared is A squared plus 5B squared. So try to solve such an equation. C squared is A squared plus 5B squared.
square.
Well, let me try to do the same kind of arguments. I can always, well, I can definitely assume that A, B are relatively prime. If they have a common divisor, this number also divides C, and then I can divide by this number. Well, once again, considerations modulo 4 show that considerations modulo 4 show that A and B can't both be odd. It's basically the same considerations. On the right hand side, modulo 4, you have A squared plus B squared. If A and B are odd, then A squared and B squared are 1 modulo 4, and then the sum is 2 modulo 4, then square root of 2 modulo 4. So once again, we can assume, A is even, A is odd, B is even. Next, let me factor the right hand side in this way, A plus square root of minus 5 times B times A minus square root of minus 5 times B. Well, I can actually factor this. How different is square root of minus 5 from square root of minus 1? Well, in real numbers, none of them exists, but we can manipulate them as if they existed and their products. Well, square of square root of minus 5 is minus 5, so we can make this factorization. It's not a factorization in Gaussian integers.
I'm just wondering, why can we assume that A is odd and B is even? Because the equation
Oh,
isn't symmetrical.
yes, so it's not symmetrical. So we cannot assume. Yes, we cannot. Okay, so one of them is A. So 1, then A, B is odd. 1 is C. So I can make this factorization, but the kind of numbers that I'm working with will be like this. It's all the integers together with square root of minus 5. It's the set of such numbers. It's x plus square root of minus 5 times y, where x and y are integers. So instead of Gaussian, sorry?
I was just telling him that you're just showing a field right now.
Well, it's not the field, but well, it's reading.
What it is the, well, it's a extension field.
It's the reading, it's not the field, you cannot divide it.
Yeah.
But the thing, these are the kind of numbers that we will be working with. So on the previous lecture, we started working with Gaussian integers. We just said that well, we'll work with a simple square root of minus 1. Well, here I'm working with a square root of minus 5. It doesn't seem to be any different. And then, well, so these are, we can give them a name, but we won't need it because we won't be working with them for too long. They turn out to be much worse than Gaussian integers actually. But anyway, so in this, we can factor any number as a product of things which cannot be factored any further in these numbers, in this kind of numbers. So we can talk about factorizations in these kind of numbers, and well, we can talk about the GCD of these two numbers. Once again, we can compute what it is. A plus square root of minus 5b, a minus square root of minus 5b. The same as GCD of the first of those, and the sum, which which is 2a. Well, 2 is a divisor of either a or b, according to this. So if it divides a plus this times b, it must divide, well, suppose it divides b, then it must divide a as well. So it's not possible GCD of these two numbers. So 2 is not the divisor of this thing, because once again, one of these coordinates is even, the other one is odd. So if you divide this by 2, you'll get half integer, not something. Not one of those numbers. Well, now you can subtract a, get that it's GCD of this symbol times b and a. Well, square root of minus 5 is definitely not a divisor of a. If a is divisible by 5, it could be divisible.
Are you not treating root of -5 as a unit? Kind of?
Yes, I'm not treating it as a unit because it's not a unit. 1 over it is not an integer here.
Okay.
So square root of minus 5 in fact could be a divisor of a. If a is divisible by 5, it's also divisible by square root of minus 5 in these numbers. Is it possible that a is divisible by 5? Well, no, it's not. If a is divisible by 5, then c is divisible by 5, and then this is divisible by 25, this is divisible by 25, this is divisible hence also by 25, and hence b is divisible by 5. So, well, let me say that it is true, and it's not hard to show that the GCD of these things is the same as GCD of b and a, which is large. So, indeed, in these assumptions, the GCD of there are no common factors of this number and that number.
So, yes, a can be divided by 5.
Yeah, so if a is divisible by 5, then you can write it as a square root of minus 5 times square root of minus 5 times minus 1 times something else, and then it's divisible by square root of minus 5.
Or if a is divided by 5, that's going to say that
Yeah, so if a is divisible by 5, then c is divisible by 5, because here we have something divisible by 5 or something divisible by 5. But then this is divisible by 25, this is divisible by 25, hence this must be divisible by 25. So that's not possible. So my point is, well, at least this is true. If a and b don't have any common factors, then these two numbers don't have any common factors among these integers, these kind of integers. The next step that we did in the previous problem is like this. Well, now we have the product. C squared is something times its conjugate, where conjugation gives, instead of plus sign here, you put minus sign here. And then you get a parameterization. Well, once again, same thing applies. We have a square is a product of two relatively prime numbers, and each one of them is a square. Z must be some square. So Z conjugate must be the conjugate of Z, and C is W and W conjugate. And you get well, you get a parameterization of the solutions. So if W is x plus I, sorry, I, not I, square root of minus 5i, y, then you get what is Z and what is C. So Z is x squared minus 5y squared plus 2 square root of minus 5 xy. And C is x squared plus 5y squared. So you get a parameterization. Any solution which is primitive is like this. A is this part, x squared minus 5y squared. B is this part, 2xy. And C is x squared plus 5y squared. So every solution which is primitive is of this form. So, well, hence kind of every solution is of this form. A, B, and C are like this. So we can copy into this board. So every solution of A squared plus 5B squared C squared is of the form A is lambda times x squared minus 5y squared. B is lambda times 2xy. And C is lambda times x squared plus 5y squared. And what's funny here is, well, first of all, these things, whatever x, y are, and whatever lambda is, they are solutions of the original equation. If you just try to plug them in, they are solutions. But, well, so you said, well, we seem to disagree that they are all the solutions. We have an example of a solution which isn't of this form. Okay, I have. So here's another solution. Let me write 3 squared as 2 squared plus 5 times 1 squared. 4 plus 5 is 9, so it is a solution. Is it a solution of that form? Well, let's try. Definitely I want C to be lambda times x squared plus 5y squared. So I want 3 to be equal to lambda times x squared plus 5y squared. Well, lambda could be 1 or 3, because this number is positive. So either lambda is equal to 1, and then 3 is x squared plus 5y squared, or lambda is 3, and then 1 is x squared plus 5y squared. No other options. But here 3 is not of this form. It's not a square plus 5 times other square. If you take the square, 0 squared plus 5, well, plus 5 is too much. 1 squared plus 5 is too much. So it's not of this form. So no solution here. And this, well, it does give you a solution. X is equal to 1 and y is equal to 0. And then this corresponds to a solution. So here x is equal to 1, y equal to 0, lambda equal to 3. It corresponds to a solution 3 squared plus 5 times 0 squared is 3 squared. So not this solution. So there is no way to get this solution, this particular solution, in this form. On the other hand, I will kind of prove to you that every solution can be obtained in this form by using factorization of these kind of strange integers together with the symbol square root of -5. I had a well factorization there, but apparently something went wrong. So I was going over the arguments kind of fast and in convenient manner, but actually the argument about GCD was correct. If A and B didn't have any common divisors, then indeed A plus square root of -5b and A minus square root of -5b also don't have any common divisors. I'm pretty sure of that. But that's not what went wrong. So maybe somebody wants to guess what went wrong.
You assume that it's
didn't assume that z is doubly square. I convinced you that z must be of the form doubly square. Here's how. C squared can be factored, well, C can be factored into the product of things which cannot be any further factored in these kind of strange integers. In these strange integers, then the factorization of C squared has only even powers of primes. But then every prime must appear either here or here. It cannot appear in both, because no number, even in these strange integers, divides both these things. Hence, every prime factor of z appears to be even power. Hence, z is the square of something. So I didn't assume this. It was not an assumption. I made a convincing argument which showed that z is square. Well, so maybe we don't see it right away, but yes.
No, they don't have to do the root of 885. It's actually root 5 times I.
Well, how does it follow anything? Because I'm not taking the factorization in total. These kind of strange integers, x plus square root of minus 5 plus y, are not even Gaussian integers. So I'm not even talking about Gaussian integers. I'm talking about this set of strange integers, these square root of minus 5. And I'm doing everything inside of this strange set. Yes? Well, well, I would say that this is a symptom, but not the problem. I mean, I did make a convincing argument to show that these are all the solutions, and yes, you make an argument that they cannot be possibly all the solutions, because here I always get even numbers b, and probably I will have solutions with odd numbers b. Here is an example. So if you are kind of making a little bit more general objection to this solution than I did, let's see, it's kind of objection to the answer, not to the solution. Well, let me take this answer and try to figure out what goes wrong with the argument. Well, if you're a computer scientist, you know that when you're programming, you might make a debug, like run over every line of code and see, well, where exactly something goes wrong. So let's make a debugging to this proof. Let's go over each line of this proof and see what goes wrong with this particular input. So first of all, I'm trying to do the following. I'm trying to say that v squared is, well, I factor the right hand side as 2 plus square root of minus 5 times 2 minus square root of minus 5. So this line is correct. 3 squared is indeed equal to this thing. Just open the brackets. It's 4 plus 5. So no problem here. Next step. I want you to prove that GCD of these two things is equal to 1. Oh, maybe this is what's wrong. Is there some number which divides both this and that? Well, we can try to check it explicitly, by explicit computation. If you have, well, maybe the norm will tell us. These are definitely complex numbers, so what is the norm of 2 plus square root of minus 5? It is 2 squared plus minus 5 squared is 9. So if there is some divisor of this number, then its norm must be equal to 3. So if z divides 2 plus square root of minus 5, and z is not equal to plus minus 1, then the norm of z must be equal to 3. Sorry, the norm is 9, it's 2 squared plus, I mean, it's like this, it's 2 plus this thing times 2 minus this thing. I mean, this thing is 2 plus I times square root of 4. So it's 2 squared plus square root of 5 squared. So it is 9. So if you have something which divides this thing, its norm must be equal to 3. But there aren't that many integers of this kind whose norm is equal to 3. The norm of something is f squared plus 5 times y squared, and well, hence basically z is plus minus 3. There are no options, because norm of x plus square root of minus 5y is x squared plus 5y squared. If you want it to be equal to 3, oh, not even this, so no such z. No such z. Because norm of this thing, if you want it to be equal to 3, there are no solutions. So even this number doesn't have any divisors which are not equal to plus or minus 1 or plus minus itself. So plus minus 1 and plus minus the number itself. So in this kind of integers, it's prime. It's not factorable as a product of anything. So the GCD here is indeed 1. Well, next step, we try to take this factorization and try the following. Let's write C as a product of primes. Let's write 3 as a product of primes. Well, but once again, 3, if you want to write it as Z and W in these numbers, then norm of Z, norm of 3, which is 9, must be norm of Z and norm of W. And we see that, well, there are no possibilities here, except, well, 3 times 1 or 1 times 3. Because there are no numbers of our kind is normally which is equal to 3. So 3 is prime in our kind of numbers. So we do have, so this thing is the factorization to prime numbers. 3 is just 3. Every prime indeed appears twice in this factorization, so it's 3 squared. On the other hand, on the right hand side, we also have a product of 2 primes. Each one of those is not divisible by anything else. But somehow, even though they are relatively prime, even though we have actual equality here, it's not true that 3 appears among the prime divisors of the right hand side. We have the same number on both sides, but it has 2 different factorization to prime numbers. So this is one factorization, this number is equal to prime number 3 squared. This is another factorization. This number is prime, this number is prime. So in this kind of integers together with the symbol square root of minus 5, it is not true that every number is uniquely representable as a product of primes. It is representable somehow as a product of primes. But some numbers are representable in many ways as products of primes. So if we have factorization on both sides, we cannot be sure that, well, all the prime factors on the left will appear as prime factors on the right. They might be just 2 different factorizations. So that's what went wrong. No unique factorization here. Factorization is not unique. It's not unique. So you see, you should be careful about these things. When you start working with, well, with funny integers, with funny objects in mathematics, you should not really assume that everything which are used to from usual integers or from whatever analogies we have apply to these new objects. Sometimes, well, stuff doesn't apply. So the plan for the next time is to actually justify why in Gaussian integers we do have unique prime factorization. Because, well, now you see that there is something to justify, it's not to make.